Hello everyone, and welcome back to thermodynamics. So we're still looking at energy transfer or conservation of energy in closed systems. And anytime we have a problem like this, there are really three questions we want to answer. The first is what's in the system. So I've drawn this system. I know there's a part of the universe that I'm interested in, and what's inside that system. So what kind of mass do I have? Is the system open or closed? Can mass come in and out between the boundary of my system and the surroundings? Now in this case, until we get past the first exam in this class, we're going to be working with closed systems, which means we can use the version of the first law that we've been talking about. Now we want to know what happens to the system, because if we understand the process where we're moving, in this case, from time 0 to time tau, then we can figure out how much heat and how much work have transpired throughout the process. And we do that using the first law. The first law tells us that the change in energy in the system is equal to the heat in minus the work out. So this lecture, we will again be looking at the first law of thermodynamics for closed systems. So we've talked about closed systems, and those are systems where mass can't come in or out of our system. So we can still have a change in volume like we see inside this piston cylinder assembly when both valves are closed. As this piston moves up, we're compressing the gas. So we can have a change in volume even though mass is not entering or leaving our system. There's a special kind of closed system that's an isolated system, and in an isolated system, the system can't interact with the surroundings in any way. So there can't be heat transfer or work that is transferred between the system and the surroundings. So what is the first law of thermodynamics? The first law of thermodynamics tells us that energy is conserved, that we can't destroy energy, that any gain in one type of energy comes at the expense of a loss of another type of energy. We talked about this big, long textbook definition, which I think is a little bit confusing when you read the words. So instead, I like to have a picture that tells me about the first law, and then also some math that tells me the change in energy that I see in the system over time is equal to the heat that comes in minus the work that goes out. We talked about how energy is measured inside of our system at two different times. So this is the total energy, and it's a sum of all the different kinds of energies that exist at particular instants in time. This energy term can be made up of kinetic energy, potential energy, spring energy, or internal energy, which is what we're talking about now. I guess that's the new part that we're talking about here in thermodynamics class. Then we have this Q term, which is heat transfer. So this is the heat transferred into the system. Remember, hip to win, so heat in is positive and work in is negative. So we've got this equation, and we have to remember our sign convention that heat in is positive and work in is negative. So the first law is important. It's an important thing for us to learn because it kind of is one of these major laws that governs what happens in the universe. So we'll use the first law in just about every problem that we do in this class, because this class is all about energy transfer. We'll use it in several different forms, but especially here at the beginning of the class, when we're talking about closed systems, we'll use this version of the equation that we've been talking about. But even when we relax that assumption and we let mass move in and out of our system, we're still using the same concept, that all energy in the universe is conserved. So here's our equation and our picture showing how we conserve energy in closed systems. We know from last class how to calculate work. So we know that that's the integral of P dV. So if I plotted my process on a pressure versus volume diagram, right? So I have pressure on the vertical axis and volume on the horizontal axis. Then the area under this curve would be my work. But in order to do that, I have to have an expression for pressure as a function of volume. And typically, we'll have an expression that looks like this, that pressure times volume to some exponent is a constant. Now we have different values for n for different types of processes. So here we got to bust out our engineering decoder rings a little bit to understand what these terms mean. So if n is equal to 0, then our equation just becomes that the pressure is constant. Now, iso means that something is constant. So an isobaric process, baric is talking about pressure, which you measure with a barometer. So here, if we have an isobaric process, that means that the pressure is constant. So when n equals 1, we get the equation that pressure times volume is constant. And this happens in processes that are isothermal. Again, iso means constant, and thermal refers to the temperature. So if you have a process where the temperature is constant, you would expect P times V to be constant. If n is equal to Cp divided by Cv, then you would expect to have a process that's adiabatic. Adiabatic is a special engineering way of talking about a system that's perfectly insulated. So that's a system where Q between the system and the surroundings is equal to 0. And if n is less than 0 or negative, then that means that Q divided by W is very high, so that the heat transfer is much larger than the work in that case. So n is not just a number that we sub into an equation, it has some physical meaning depending on the value of n. So we know how to calculate work. We're going to learn in the next class how to calculate this change in energy. But what we know about delta E so far is that delta E is really talking about the change in all kinds of different energy types. Changes in kinetic energy, potential energy, spring energy, and internal energy. So here, if I sub my expression for E2 minus E1 back into my equation, I get something that looks like this, recognizing that the change in the total energy is the sum of all the different changes in different types of energy. So in thermodynamics, we'll often make several different assumptions about these different energy changes. So oftentimes we have a change in kinetic energy that's much smaller than this change in internal energy for the processes that we'll talk about. Things like, how do you look at energy that's created from internal combustion engines or nuclear power plants? We have the same thing for changes in potential energy. While things might change in their elevation, we typically see in the processes that we're talking about that this change is small relative to changes in internal energy. The same thing goes for spring energy. So in thermodynamics, we can simplify this expression we have for the first law for closed systems to something that looks like delta U, which is the change in internal energy, is equal to Q minus W. So now we have this first law, and there's three terms. We know how to solve work. We're going to learn how to solve this change in internal energy next class. And typically what we're going to do is we're going to fix states, and we're going to say the change in delta big U, which is internal energy, is going to be the mass in my system times the change in the specific internal energy. So to get from a property, in this case internal energy, to the specific version of the property, specific internal energy, you divide by m. And that's nice because when we have specific internal energy, it means that that's a property we can look up on a table, and it's independent of how much mass you have inside your system. We're going to learn about how to find specific internal energy next class. So if I have this version of the first law and I can find work, and I can find the change in internal energy, then I can use the first law to find the amount of heat that's transferred in my process as I move from state 1 to state 2. Of course, you can have problems that go the other way, where maybe we're calculating work and we're given heat transfer, and we can use that to find the change in internal energy. Here we have another example problem. The problem says a gas in a piston cylinder assembly is compressed from one pressure at a volume to a second pressure in a process for which the relationship between P and V is PV to the power of 1.2 is constant. The mass of the gas is given. During the process, the heat transfer from the gas is 2.2 kilojoules. Determine the change in the specific internal energy of the gas in kilojoules per kilogram. Kinetic and potential energy effects are negligible. So let's do this problem together. So we have this problem, and this is what our PV diagram might look like. We go from V1, which is the larger volume, down to V2. So we're compressing the system. So we're putting work into the system. So we would expect from our sign convention that work in is negative. We're putting work into the system. So we're expecting negative work in this problem. So now we know the governing equation delta U is equal to Q minus W. I can find my work. That's the integral of P dV. I'm trying to find delta U, so I won't have to do this, but in normal cases, we would find the change in specific internal energy, multiply that by the mass, and use it to get Q. But in this problem, we'll find the work. We know Q because it's given in the problem, and then we can use that to find delta U. So here we're required to find the total work. That's the first thing that we need to find. So we know that work is the integral of P dV. Now we're told that P times V to the power of 1.2 is constant. Or I can rearrange that to see that P is equal to some constant divided by V to the power of 1.2. So if I put that into my equation, because C is constant, I can bring that out of my integral, and I can see that work is equal to C times the integral from V1 to V2 multiplied by V to the power of 1.2 dV. If I do the integral, it looks like this. Now, because I have bounds on my integral, I can do some math and find out that C divided by negative 0.2 is equal or multiplied by this difference of these two fractions. Now, I don't really like my term outside the brackets being negative. This is just a personal preference. So I'm going to multiply both the term inside and outside the brackets by negative 1. So now my term outside the brackets becomes positive, and I alter the order of the two terms inside my bracket. So this is nice. I know V1 because it's given in the problem. I don't know V2 yet, and I don't know C yet. So what do? I'm always going to advocate that you should try to solve problems symbolically when you can. You can find a numerical value for C, but I'm going to show you a little bit of sleight of hand here to demonstrate that it's nice if we keep symbolic solutions here for as long as we can. So here you might remember that the problem tells us that P times V to the power of 1.2 is constant. And if that's true, then that means P1 times V1 to the power of 1.2 is equal to that constant C. But that constant C is also equal to P2 times V2 to the power of 1.2. Now, I can rearrange my equation above, and I can just multiply C back into my bracket here. But I know that C can be the left-hand side of this equation or the right-hand side of this equation. So now I put in two different symbolic versions of C because I want to be able to factor out V1 to the 0.2 and V2 to the 0.2. Now when I do that, I get that work as we go from 1 to 2 is equal to 1 over 0.2 multiplied by P1V1 minus P2V2. I still don't know V2, but now C doesn't appear in my equation at all. So now I've gone from two unknowns to one unknown. And I have a pretty clean looking equation. So now I got to find V2. And again, I can use this relationship that P1 times V1 to the power of 1.2 is a constant, so it must equal P2 times V2 to the power of 1.2. So I can rearrange this expression to find an expression for V2. Now, I can put in my values that I have in the problem. And the nice thing here is, because I've put this equation as a ratio of P's, and it looks like this should be P1 divided by P2, so there's a bit of an error in this case, but I fixed it down here when I did it numerically. Now, it doesn't matter what units I use for pressure here, as long as it's absolute pressures, because as long as they're the same, it works out. So I could change this to bars or atmospheres or pascals or kilopascals, but the ratio is going to be the same. So I'm going to leave it in bars for now. Those bars are going to cancel. And when I put that into my calculator, I see that V2 is equal to 0.136 cubic meters. So this is good because my volume is getting smaller, which is how I drew it out on my picture. So now V2 goes from unknown to known. So now I know everything that I need to know to find the work. So work is equal to this equation here when I put in the values that I know from my problem. So here I've changed from bars to kilopascals by multiplying by 100. But I see here that I'm going to want to multiply the kilopascals by meters cubed. So I'm going to change 1 kilopascal is equal to 1 kilonewton per meter squared. So I'll put that in here. And that means that as I'm carrying my units through, I see that both of these terms in my bracket are kilonewton meters. Now I remember that a newton meter is a joule, so a kilonewton meter must be a kilojoule. So when I do this, I see that the work, as I go from 1 to 2, is negative 76.6 kilojoules. So does that make sense? So we know that the units are correct because we're talking about work and we're getting an answer in joules. I know that the sign is what I expect because I'm compressing my system, so the surroundings are doing work on the system. So I expect this work to be negative. So the units are right and the sign is right. And that gives me some confidence that my expression for work looks pretty good here. So I don't know if the magnitude of the work is correct, but I do feel pretty good about my answer because the units and the sign make sense. But this is not what the problem asked me for. The problem asked me to find the change in the internal energy. So I need to go back to my first law. So if I make the assumptions that kinetic and potential energy changes are negligible compared to the change in the internal energy, then I get this equation. And now I know the work, and I'm told in the problem that the magnitude of the heat transfer is 2.2 kilojoules. But my first law equation doesn't ask me for the magnitude of Q. I need to know the sign. The problem tells me that heat transfer from the gas is 2.2 kilojoules. So when I read this, it sounds to me like the gas, which is my system, is losing heat. And I know from my sign convention that heat in is positive. So heat out, which I'm seeing in this case, must be negative. So my Q term is negative 2.2 kilojoules. There's two things that I like about this. First is that my units are units of energy, so that makes sense for Q, and it's the same units for work. So I have both of these energy terms in kilojoules, so I don't have to do any conversion. It's not like one is in joules and one is in kilojoules. So now I know both my terms on the right-hand side, and the problem has asked me what the change in internal energy, or the left-hand side of my first law equation is. So now I start with my first law, and I sub in the information that I know. So I know that Q is negative 2.2 kilojoules, and I know that work is negative 76.6 kilojoules. Now, one of the things that's easy to mess up if you move too quickly through these problems is to forget that this is negative W. So negative W, so here we have negative of a negative number. So this is going to become a positive term here at the end. And again, if we move too quickly, we may have got the sign for Q wrong as well. So remember, we got to act like Dora as we're completing these problems, and we got to stop and think. This is a really good practice for engineers, no matter what we're doing. So when I put this stuff into my calculator, I see that the change in the internal energy is a positive value of 74.4 kilojoules. Now I got to ask myself, does this make sense? So U, capital U, is internal energy. So the units should be energy, right? And that's what we see here because we have kilojoules. But does it make sense that the sign is positive? So assuming that I got my magnitudes of Q and W correct, I see that the work is much more important than the heat transfer in this case. So the heat transfer is negative. So my system is losing energy because it's losing heat. But it's also gaining energy because we're compressing our system. So the energy that the system is gaining from the work is much larger than the energy term of the heat loss here, right? So it's kind of the work that dominates this problem. So it does make sense that U2, the energy in my system at the end of the problem, is bigger than U1 because the work we're doing on the system is bigger than the heat that we lose from the system. So that's the end of this lecture, and hopefully you're starting to get some kind of understanding of how we do first law type problems in closed systems. Next class, we'll learn a little bit more about how we start to find specific internal energy so that we can find delta U in problems like this without knowing the heat transfer. Thanks again for joining us on Thermodynamics. I'll see you next time.